Well, hello and welcome back to statistics and a thrilling, let me get rid of this right here, and another thrilling rendition into statistics. I can move this around a little bit. Don't pay attention to this over here right now. So we're in chapter 17, and in chapter 17, we need to talk a little bit about what it means to be a parameter of interest and how to determine if we're doing a confidence interval or if we're doing a hypothesis test. That's really the goal here in this particular section. My setup here has changed a little bit since the governor has locked me down at home. I can't get into my building. And so I have to change the way I'm doing things a little bit, and hopefully that they're going to work out okay for us. And give me feedback and let me know if there's a problem. So let's talk about confidence intervals first. That's our first discussion. Remember that when we talk about a confidence interval, we're discussing a range of plausibility, okay? A minimum and a maximum. Think about the speed limit on a highway, and if you have a minimum speed of 55 and a maximum speed of 75. We can almost think about that like a confidence interval. And in a confidence interval, this particular piece of paper here shows us, okay, there's a clear difference between one population and two populations. And all of this is meaningful information and goes from a single mean to a single proportion and a difference in means and a difference in proportions. And ultimately, at the end of the day, what we're looking to get down to is we're looking to get down to the formulas. And these formulas, are down here for confidence interval levels. And each one of them goes with a different example. Like, for instance, a single mean would be right here. And a CI for a single proportion would be right here. And a CI for a difference in means would be right here. And a CI for a difference in proportions would be right here. And we'll have to come back and we're actually going to have to talk a little bit more as we get to these. But for right now, we're going to use this as a guideline, okay? And we're going to come back and do some of these in a second. So as we switch, notice the page changes, and in the page changing, now we're talking about a hypothesis test, something for which we are seeking evidence, looking to see if a particular amount of arsenic in chicken, as we've discussed, is greater than some number. That's a test. And that test will be into three different categories. And we've talked about these three different categories. Is it a right tail, greater than? Is it a left tail, less than? Or is it a two-tail test, just simply not equal to? And again, the same criteria here on this particular page is we might have one population and we might have two populations. But down at the end of the day, and we will use all the information in between. Don't let me minimize any of that. But today we want to focus on the formulas. And I want to call special attention to this last particular formula here, to where there's an embedded part of this formula which calculates what we call pooled proportions. And these values that I'm underlining, notice they're not P1 or P hat 1, P hat 2, they're just simply P hats. Those P hat values are referred to as pooled proportions. This happens under a statistical test for the difference of two proportions, in which we have to do a calculation in order to insert it into another calculation. And we will do those. Today, all we're going to do is we're going to set up these values. We're going to go through these questions in the scenario. And in the scenario, we're going to figure out, okay, what is it that we actually have and which formula will I be utilizing? Okay. I am going to, for the sake of all individuals involved, I'm going to use my my web capture here, and I'm going to try and capture a little bit better over here as we're working. So I'm going to flip through and talk about these. And this is the same thing as on the screen, and hopefully you can blow up one or do another one, but I can write a whole lot better over here than I can on the paper itself. Okay, and I'm going to switch and see what happens here. The next one, I may just go full screen on this completely and leave behind the PDF. So first of all, it says, answer each of the following questions in examples. Does the scenario represent a confidence interval, or is it a hypothesis? That's our first thing to check. Is it one population? Is it two populations? What's the appropriate formula? Okay, so we'll go back to that formula sheet. And what does each symbol represent in the formula sheet? Okay, so let's find the important information here. So first of all, in a sample of 120 boxes, okay, so we have a sample of 120 boxes. Okay, that's important. Of rice produced in the U.S. shows an average 2.3. That's an X-bar statistic right there. These are exactly how I would answer the question if I were a student looking at this particular question. Pounds with a population standard deviation, here we go, population standard deviation of 6 ounces. Determine a 95% CI, right there, for the mean weight for the population of boxes of rice produced by the company. Okay, so we have one mean is what we have, and we're building a CI from one mean. So we go to our formula sheet, and I'm going to bring that up over here on the computer. We go to one single mean, confidence interval level, and this is the formula that we're looking for. So our formula is going to be X bar plus or minus this thing called T star. Well, T star is a lot like Z star, which we have calculated already. You don't know how to do T star yet. I'll show you soon, though. And we're going to multiply that by the standard deviation divided by the set of n. Now, remember, we know what these means. It says we should, what do these mean? This is the statistic, 2.3. T star, you don't know how to get that yet, but you will pretty soon. S, standard deviation, 6. Root of n, how many things did you measure? 120. So if we filled in what we know right now, we know 2.3. We don't yet know T star. We do know S is 6, and we know that the sample n was 120, and it's a square root of. Let's go to the next one. I'm going to lighten up my exposure just a little bit to make it brighter, hopefully. So here we go. Next one. So first of all, we're testing. The word test right there, that right there tells me it's not a confidence interval. This is going to be a hypothetical test. Okay. Test whether males are less likely, so we want something less likely than females, so there's my second object. If 24%, well, 24% means a proportion, right? So this is a p hat of a random sample of 50 males plan to vote yes on the initiative, and 32% of females, of 50 females, plan to vote yes. All right, well, first of all, it's a test. So it's no longer a CI. Now we're talking about a hypothesis test. We also have two populations. So I know I'm doing a hypothesis test. I know I'm doing two populations. So I go to my piece of paper over here, hypothesis test. I go down to two populations, and I've got this beastly formula right here, okay? So first of all, I'm going to look and see what I have in this. So the formula I'm utilizing is, oops, sorry, I was off the screen there, is going to be Z equals P hat of 1. That's the proportion of set 1 minus the proportion of set 2 minus 0. Why 0? That's the null hypothesis. Remember, nothing going on. Divided by great big square root here. We're going to have P hat. Notice it's not P hat 1 and it's not P hat 2. It's P hat. That's the pooled proportion right there. Times 1 minus the pooled proportion over N1. That's the number of items in set 1. Plus P hat 2, or excuse me, P hat, again, pooled proportion, times 1 minus pooled proportion divided by the set of N2. We're not going to fill in formulas right now, but let's talk about what they are. P hat of 1, 24%, 0.24. P hat of 2, 32%, 0.32, minus 0. Pooled proportion. Well, in order to do the pooled proportion, we're actually going to have to use that calculation. So we're going to have to go off to the side, and we're going to have to take, okay, the percentage, the n value, the number of set 1, times its proportion, plus the number of things in set 2 times its proportion, all divided by the pooled value of proportions, which is actually P1 plus, or excuse me, N1 plus N2. That's a lot of stuff. Right now, we're just trying to figure out, okay, what goes where, okay? What goes where? Let's look at student exercise 3. So in student exercise 3, the owner of a fast food chain states that they would be willing to build one of his restaurants in a certain city if more than 30%, right there, if more than 30%, that right there makes it a test. Of potential customers indicate that they would be willing to try the restaurant after it is built. In a sample of 600, there's your n value, 600, 220 indicate that they would try it. So 220 is going to be my proportion of 600. So first of all, I know some things here. I know my sample statistic is 220 out of 600 people. That's the same as 0.37. If I was writing my H sub O, remember my null hypothesis, then my proportion would be equal to 0.3. Nothing going on, 0.3. My H sub A, my proportion, remember, more than, I want it to be more than 0.3. So we're doing a test here. And in this particular test, we're going to go back up to, I'm going to scroll back up. And we're testing, so we want to be on hypothesis testing. We're talking populations, and the population we're dealing with is a statistical test for a single population. We don't have a mean. We're not using this one. We have a statistical test for a single population. The population is 0.37. So let's actually fill out the numbers for this one. So we're going to use Z equals P hat. P hat is 0.37 minus, remember, it's P sub O, and P sub O means P of nothing going on. Nothing going on is 0.3. P sub O is always the nothing going on or the null hypothesis, the H sub O. In the bottom of this, we need a root. We're supposed to take P sub O. P sub O is 0.3, the null, times 1 minus the null, which is 0.7, but we're going to write it as it is, divided by n, and n was the complete number of sample, which came to be 600. Put that in your calculator. See what you get. Let's go to the next one. So we're on exercise number 4. Hopefully this is working out for you with me using the dock camera. And I think on the next one, I think I might just go straight to the dock camera instead. To the last one. It says the average daily, right there, that's a key terminology. Average daily telephone usage. That's a measurement that's in X bar. Okay, X bar. Of hotels in the United States is 3 hours and 10 minutes. Okay, so all hotels in the United States are 3 hours and 10 minutes. Now remember, when we write that, that's going to be 3 hours and 10 over 60, 10 minutes out of 60, or 3 1/6. 3 1/6 hours. Okay. It says a sample of 45. That's important. Sample of 45. So I'm going to write that down right now. N equals 45. I also know this. I'm going to write this down. This is my mu value because this is all. Mu is 3 1/6. Show that Ohio average is 3 hours and 40 minutes. Okay, well, that's my X bar. X bar is 3 40/60ths. 40/60ths, which is 4/6, which is 2/3. Okay, I got 3 2/3 because I took 40 out of 60 minutes, and 40 out of 60 minutes is 2/3 of an hour. Don't use 0.6 repeat or 0.6. And the last thing I need to know here is that a minutes of standard deviation of 35 minutes. Standard deviation. Since all these measurements up here are in hours, then we have to write our standard deviation in hours, and that's 35 out of, oops, sorry, I wrote 35. 35 out of 60, and yes, you can reduce that just fine. 5 goes into the top 7 times, and 5 goes in the bottom 12 times. So which formula are we going to use here? All right, well, first of all, it says we are interested in determining whether or not the average ozone dose is significantly different from the U.S. average. Are we significantly different from the U.S. average? All right, so remember, we're going back up here, and we're talking about mean values here. Okay, we're talking about mean values. We're doing a statistical test, and we don't have two different means. We have a single test for a mean value. So if we take the statistical test right here for a single mean, t, so I'm going to take t. I'm going to put t equal to my first value, which is x, my statistic. My x statistic is 3 2/3. I'm going to subtract my null, or my mu. My mu value is my null, really, because it's where all states are. The U.S., 3 1/6. I'm going to divide that by the standard deviation. Well, the standard deviation is my 7/12 of an hour. And that 7/12 of an hour has to be divided by the root of n, and n was 45. You can certainly practice putting these in calculators. Last exercise, number 5. In a survey of 1,000 U.S. adults, 20%, okay, 20%, that makes it a proportion right away. P hat is equal to 20%, or 0.2. Say they never exercise, and it was out of 1,000 N's. Find a 99% confidence interval for a proportion of U.S. adults who say they never exercise. Okay, so we're looking for a CI. So we go to our CI, and remember in the CI, we're talking proportions here. Okay, so I got to get up to CI, confidence interval levels. I have a population proportion, a single proportion, and I am looking at the conditions straight down here. Okay, so we're going to start our measurement with p hat. Okay, well, our p hat, you can write that two different ways. Depends on how you want to do it. Your p hat value plus or minus your z star. Remember, we know how to get that right there. Times the root of p hat times 1 minus p hat. And that's going to all be divided by n. Okay, so our p hat value is either this value or, remember, it was 20%. Well, 20% of 1,000 is 200 over 1,000. But remember, if you start slashing out zeros, you got 2 over 10, you got 0.2. So using this is kind of cumbersome. Probably want to use 0.2, right? Plus z star. Well, remember, you already know how to calculate z star. We've done this in our calculator. we go and we find the area of the 99%. Remember, that's 1% at each end, or excuse me, that's 0.5% at each end because it's 1% combined. And we found that number to be 2.576. You have to remember how to get a z-star from the last chapter so you can work this formula. Multiplied by, well, remember we have our p-hat. Our p-hat is 0.2 times 1 minus 0.2. Yes, I could write 0.8, but I'm going to write what the formula says. And I'm going to divide that by n, and n was 1,000. I'm going to stop the video. I'm going to go back and I'm going to do each of those calculations so you can check them with your calculator so you can see if you're doing okay. So I'm going to, again, I got to stall my video for 1 second, and then I will put all the answers up for you. And as promised, here are my answers. Number 2, I was looking for a z answer. My calculations, z negative 0.891. So I'm the left side of the center, less than 1 standard deviation away, because remember that's what a z-score means. Number 3, I have z value of 3.742. I am far, far, far to the right of 0. Number 4, I did a calculation. Watch this one right here, 35 minutes out of 60, because it was a 35-minute standard deviation, 5.750. And my last one, number 5, I had to do a plus and a minus version to get a CI. So I used the formula with the minus to get 1.67. I used the formulas with the positive to get 233. That's not a negative sign. It's a from here to here value.